Welcome to week number 11 of ECE 111, Introduction to ECE. This week, we're going to look at inductors. Now, last week, we looked at capacitors. Capacitors are integrators. If you have an RC circuit, it behaves like the heat equation. For example, this is what we looked at last week. If I have a 10-stage RC circuit, and I give it a step input, this is how it behaves. That's also how temperature behaves. If I have a long metal rod, where's the temperature at the base? The temperature propagates down the rod according to coupled first-order differential equations. That's the heat equation. Today we're going to look at inductors. Inductors behave very differently. Those give you coupled second-order differential equations. When you do that, you get the wave equation. It behaves very, very different than the heat equation. So that's what we're going to look at today, is inductors. Now, starting out, an inductor is something which stores energy in magnetic fields as opposed to electric fields, like capacitors. For inductors, the units are henries, and one way to make an inductor is just wrap wire around an iron core. That makes it an electromagnet. That also makes it an inductor. For example, this is an electromagnet. Just take a bunch of wire, wrap it around a piece of iron, put current through the wire, and you have a magnet. And you also have an inductor. So inductors and electromagnets are really the same thing. Whatever stores energy in a magnetic field is an inductor. So to give an idea of how to calculate the inductance, suppose I have 100 windings of 36 gauge copper around a tube, hollow tube filled by air. Assume the tube is 1 inch diameter. The length of the inductor is 10 millimeters. The inductance is calculated by this formula. It's a constant mu times the number turned squared times the area, cross-sectional area, divided by the length of the inductor. Plugging in numbers, this is the constant mu, it's just a natural constant, times the number of turns squared, the area, length, I get 31 microhenries. So inductors, like capacitors, tend to be very small. Typically, inductors in the order of microhenries, occasionally get up to millihenries. 1 Henry inductor is actually pretty big. One problem with inductors. This is a long strand of wire. Wires inherently have resistance. So that 100 windings of wire also has resistance calculated out of 2.77 ohms. So unlike capacitors, which are pretty close to ideal, inductors almost always have resistance involved. So a 31 microhenry inductor, fairly small, has 2.77 ohms resistance in this case. This is something I don't like, but you're kind of stuck with it. This is one of the reasons we don't like inductors. They have inherent resistance. You encounter inductors all the time. Anytime you have a magnetic field, you're storing energy in the magnetic field, that's an inductor. So for example, if I just have transmission lines, when I have current going through a transmission line, that produces a magnetic field. That magnetic field stores energy, meaning a wire is an inductor. From Wikipedia, you can calculate the inductance per unit length. Here's the equation from Wikipedia. This is the constant A, B, and C, function of the parameters of the wire. Net result is the transmission line would have an inductance of 2.3 millihenries per kilometer. May not seem like much, but over 1,000 kilometers, that adds up. In terms of characteristics for inductors, inductors store energy in the magnetic field. The energy stored is 1/2 Li squared. The power is the derivative of energy. So I take the derivative. When you get to calculus, you'll see that the derivative of I squared is 2I. So this becomes power is volts times amps. That's Li di dt. Again, the 2 cancels with a half. Cancel the i's, and you get the VI characteristics for an inductor. V is L di dt. So last week we looked at capacitors. For capacitors, voltage is 1/C times the integral of I dt. Capacitors are integrators. Inductors are differentiators. So for example, suppose I have the current going through the inductor as the red line. The voltage will be the derivative of the current. So when the current is 0, the voltage will be 0. As the current increases, the voltage shoots up by the slope, goes up by 3 amps in 1 second, slope is 3. Since the inductance is 1 Henry, the voltage will be 3 volts. When it's constant, the voltage is 0. Negative voltage means the current's dropping. Well, current's dropping means a negative voltage. Constant current means 0 voltage. So, unlike capacitors, inductors are differentiators. Capacitors are integrators. So, if I have circuits with inductors, they behave very different than circuits with capacitors. Going back to last week, if I have a capacitor, again for capacitor, I equals C dB dt, the current I1 is the current from the left plus the current up. Current from the left is V0 minus V1 over 30. Current up is 0 minus V1 over 150. Plug in numbers. An RC circuit is satisfied by first order differential equation, heat equation. This is for one element. What this means is if the input is a square wave, I'm going to charge up the capacitor, discharge it, charge, discharge. That's how the heat equation behaves. That's how capacitors behave. In contrast, if I have a couple second order differential equations, I get the wave equation. An example of that with just a single term would be a mass spring system. For mass spring system, force is mass times acceleration. The net force on the mass is the force that I apply minus the spring constant times displacement. So if I pull the mass to the right, the spring is going to pull me back left. That's the minus sign. If I push it left, the spring is going to push me right. So the spring is always opposite the direction of motion. That's the minus sign. And for springs, the force is proportional to distance. If I solve for the acceleration, plugging in numbers, I might get something like this. This is a second order differential equation. The way that behaves is, well, think about it this way. Take a mass on a spring, pull it down, it's just going to bounce up and down. Unlike the heat equation, this oscillates. Very different. If I put a bunch of masses together, it's just like the heat equation, except that instead of the first derivative being terms like this, it's now the second derivative, the acceleration. So coupled second order differential equations gives you the wave equation. And that equation appears all the time. You see that in transmission lines that are galloping on windy days. You see that in cars stuck in traffic. You see that in buildings swaying in the breeze. You see that in bridges oscillating during windstorms, and so on. That's the wave equation. That's coupled second order differential equations. To give a couple examples, here's a couple videos to watch. Oops, get through the ads. So for example here, this is a windy day out in the country. I see the transmission lines hopping up and down. What's happening is the wind provides a force on the wires. That's a force. Force gives you acceleration. Acceleration integrate twice gives you position. That's second order differential equations, and this is a whole string of them along wire. The way that behaves is very different than the heat equation. They bounce up and down. Second example. Car stuck in traffic. So here, if you're accelerating based upon the distance between you and the car in front of you, the acceleration, second derivative, is proportional to distance. And what you get is stop and go traffic. You get these standing waves. You would think that the cars would just move at a constant speed. They don't. With no obstructions, nothing to stop the cars, you're getting stop and go traffic. Third example, where you see the wave equation. This is a famous example, Valparaiso Bridge, or Tacoma Narrows Bridge. The wind is blowing the bridge. That's causing acceleration with turbulence. I get a standing wave on the bridge. Rather than the heat equation, which just heats up, cools down, with the wave equation, you get these oscillations. That was enough to make the bridge fail. One more example. This is an earthquake. And you see the buildings swaying in the breeze. The earthquake is shaking the buildings. The buildings act as a large mass spring system. I've got mass, which is second derivative to get acceleration to position, and the spring constant. As you twist the building, or as the building sways, that's your spring. Trying to bring it back and forth, you get swaying buildings. Those are coupled second-order differential equations. That's the wave equation. And you see that all the time. So some of the places you see that in the ECE curriculum, these are the courses you need to graduate for computer engineers, similar for electrical software engineers. You start out in Algebra 1, solving one equation, one unknown, get to trigonometry, sines, cosines, and circles, calculus, differentiation, Calc 2, integration. At that point, you get into Circuits 1 and Circuits 2. Circuits 2 are where we introduce inductors. Those are used a couple different places. They are used, just going over to electrical engineering, they were introduced in Circuits 2. They're used in 351 electromagnetics. When you have a long wire, it has inherently inductance. Again, wires store energy magnetic fields, that means inductance. If I have a wire and a ground plane, that's a capacitor. This is the electrical circuit for a wave equation, something we'll talk about in a second. This is what we study in electromagnetics. In energy conversion is all about motors. Motors are electromechanical devices. With the electric fields, you get inductors. So inductors are also studied here. So you're going to see inductors and the wave equation a couple times. And they behave kind of weird. With MATLAB, I kind of show you how coupled second-order differential equations behave. To start out, I need to come up with the mathematical equations for a typical wave equation. In this case, I'm going to take a long transmission line, just basically a long wire, like a transmission line. If I have a long wire, it has inductance. Those are your L's. If this is the ground, I've got a parallel plate capacitor. That's your C. In addition, if this is like a galloping transmission line, bouncing up and down, there's wind resistance. I'll model that as a resistor R. So this would be the circuit equivalent for a transmission line bouncing in the wind. This is also a circuit on a circuit board trace, stuff like that. Let's come up with the equations for it. The trick is for inductors, the voltage across an inductor is L di dt. For a capacitor, the current to a capacitor is C dV dt. So the basic equations are the voltage V1 minus V2 is L di dt, V3 minus V2 is L di dt, and for the capacitor, IC is C dV dt. IC is I1 plus I2 minus this current, minus V2 over R. So those are the basic equations. To simplify, there's a couple ways to do it. One trick is to take the derivative. Differentiating this, I get the second derivative of V2, first derivative of I1, first derivative of I2, and derivative of V2. Now solving for I1, you bring the L2 right, and substitute for I2, dot, and now rearrange the terms. I get this is the equation for node 2 of this transmission line. Notice it's very much like what we had before for the heat equation. The difference is the result is the second derivative. Instead of giving you the heat equation, that gives you the wave equation. If I have a couple terms, like a 3-node wave equation, what I'm going to get is at node 1, I get V1, second derivative, is 1 over LC times V0, this is V0, 2 over LC times V1 minus 2 over LC, plus 1 over LC times V2 minus 1 over RC times V1 dot. Likewise at node 2, likewise at node 3. Node 3 is a little bit of an oddball. There's only one inductor attached, so rather than getting 2 right here, I just get 1. If I plug in numbers, I get my coupled second-order differential equations. Now to solve these, that's a little bit of a trick to solve by hand, but MATLAB's here. With MATLAB, I can solve second-order differential equations. The idea is, just like we did last week, integrate once, I get the first derivative, but now I integrate a second time to get voltage. In MATLAB, I can do that as follows. I'm going to specify the initial voltage, the initial derivatives. At any given time, I'll calculate, this is the second derivative. Now integrate. Integrate the second derivative, I get the first derivative. Integrate the first derivative, I get voltage. Now plot the voltage. And let's see how that works. So here's the MATLAB file. I calculate the second derivative, integrate to get the first derivative, integrate to get position. And I'm going to give it a step input. Initially everybody's 0. The voltage on the left goes to 100 volts. What happens? So when I run that, okay, note this is very different than the heat equation. Heat equation, I would just charge up to 100 and stay there. Wave equation doesn't do that. Instead of charging, it just bounces up and down. After 10 seconds, if I plot it, instead of getting a nice charge, discharge, I get a very different response. That's the oscillations. What you're seeing is kind of like the bridge oscillating in the wind. You see the galloping transmission lines. You see the building swaying back and forth with an earthquake. That's the wave equation. In terms of why it's called the wave equation, that shows up better if I increase the number of nodes. So if I repeat for 30 nodes, what I get are 30 coupled second-order differential equations. Now, the first 29 are very similar. It's the same pattern of 50 minus 150. So at any given node, I've got an inductor connected to the node to the left. This is 1 over LC. An inductor to the right, 1 over LC. And at the given node, I get 2 over LC. I've got a little bit of resistance right here. That's this term right here. That repeats the first 29 nodes. The last node is a little bit different. I only have 1 over LC. So basically, I lose 100 units of current on node 1. 50 goes left, 50 goes right. At node 30, I lose 50 units of current. All 50 goes left. There is no right. What that does is that creates a traveling wave. So I can see that in MATLAB. I'm going to go over to MATLAB. This is the same thing with 30 terms. Now instead of doing 30 copies and pastes, I'm going to put that in a for loop. So for nodes 2 to 29, I get this equation, 25, 50, 25. If I run that, here's what I get. So the voltage on the left was that little snap. What that did is that launched a wave, which is why it's called the wave equation. Now if you notice, there's a thing called a reflection coefficient. When I launch the wave, when it hits the right-hand side, I get a plus reflection. So here's the negative wave going to the right. It hits the right wall, reflects. Let's try that again. I launch a wave. The wave travels down the transmission line, hits the right wall, and it reflects. That is a plus reflection. When I hit the left wall is anchored at 0. When this is anchored, I get a negative reflection. So with wave equations, I get reflections. There's a thing called a reflection coefficient. It tells you how big that reflection is. Those reflections cause trouble. Those reflections are what's causing the things like the bridge to sway in the breeze, the transmission lines to gallop. The energy is traveling down the line, and instead of dissipating, it just keeps bouncing back and forth. To calculate the reflection coefficient, there's a thing called gamma. That's the reflection coefficient. It's a function of the impedances. When you have a very large resistor, meaning, well, when R is very large, this right endpoint is free to move. Basically, large resistance means basically no friction. The right endpoint moves freely, I get a plus reflection. When the right endpoint is very, very stiff, I get a negative reflection. I can see that in MATLAB. Going over here, again, for the simulation I'm doing 25, 50, 25, same idea. This guy right here is the resistance, the losses at any given node. This is the loss at the end node. If I make this a very lossy line, let's slide over. Let's make this 1. What this means is I've got a transmission line traveling through molasses. It's really lossy. I launch a wave, and you can see it dies out. So this would be a galloping transmission line in molasses or in water. So let's bring that back to 0. Change this number right here. This is the very last node, node number 30 or node number n. When this number is really small, let's just go for 8 seconds. When that number is really small, what happens is the right endpoint is very free to move. There's basically no friction. When it's free to move, this moves up and down freely, like a better word. I get a plus reflection. Okay, suppose I make this really, really big. Let's try 100. So this means I've got a very stiff right endpoint. Stiff would mean the right endpoint barely moves. If I launch a wave, travels down the transmission line, hits the right endpoint. Now the right endpoint will barely move because I've got a big resistance. I get a negative reflection. Let's do that again. Launch a wave. Wave travels down the transmission line. Hits the right endpoint. Right endpoint barely moves. This brings up a question. What's the Goldilocks value? So if the right endpoint is too loose, I get a plus reflection. If it's too stiff, I get a negative reflection. When do I get no reflection? That's actually an important question to ask. What that means is on bridges. If I take the two endpoints in the bridge, which cause the waves to reflect back and forth, if I make them really, really stiff, I get standing waves. If they move freely, I get standing waves. How much friction do I add? How stiff do I make the ends of the bridge so I don't get reflections? Likewise on skyscrapers, likewise on transmission lines, likewise on circuit board traces. Well, in MATLAB, when you take the course EMAG, you can calculate that. Here, I can use trial and error. So 100 is too big. Let's try 30. When the stiffness on the right is 30, this is 1 over RC is 30, so this number is getting bigger, R is getting smaller. No, R is getting bigger. I still have negative reflection, so 30 is still too big. Let's try 3. You can actually calculate what this number should be. When you take electromagnetics, you'll calculate that. Here, using MATLAB, I'm just going to use trial and error to find it. At 3, that's pretty good. That's still a slightly plus reflection. So 3 is a little bit too small. Let's try 7. Wave goes down to the right, hits the right endpoint. Slightly negative. Okay, let's try 6. There is a theoretical number that you need. From a practical standpoint, you don't have to be dead on. If instead of absorbing 100% of the energy, I just absorb 90%, that's still pretty good. And that looks about right. So this is say I want 1 over RC to be 6. That gets rid of most of the reflections. To see what that does, if I take the input and instead make that a sine wave, we get standing waves. For example here, the input is a sine wave, just going up and down. That'd be like an earthquake shaking a building. I have the right point is too small, the resistance is too large. What happens is I'm launching waves from the left, I get reflections from the right. When the two waves collide, I get standing waves. That's kind of what you see with galloping transmission lines. So if I make the right point too small, I get reflections. If I make it, or standing waves, if I make it too big, I get reflections. So here, I made the right endpoint too stiff, so the right endpoint's just barely going to move. And once again, you'll see I get standing waves. So I hit the right endpoint, it barely moves, that causes a negative reflection. The reflections from the right plus the wave from the left give you standing waves. Again, that's kind of what you see in the Valparaiso Bridge. I get standing waves, that's going to cause the bridge to collapse. You see that on skyscrapers. To get rid of that, what I really need to do is get rid of reflections. So 6 was about the number that I found. There's your standing waves. Try to get at 6. What happens is instead of getting reflections, all the energy is absorbed on the right. If there's no reflections, there's no standing waves. So this is really what you want for a transmission line. This is really what you want for a building. And there's your second order couple differential equations, the wave equation. So, I guess we kind of talked about that. There's a couple reasons why reflection coefficients are important. The wave equation models a large number of things. It models cars stuck in traffic, buildings swaying in the breeze, bridges oscillating during windstorms, transmission lines galloping on windy days, long electrical transmission lines, circuit traces, and so on. The reflections create standing waves that results in traffic coming to a standstill, clogging freeways, bridges swaying and collapsing, bridges oscillating then collapsing, or buildings swaying, transmission lines galloping, hitting each other and snapping due to metal fatigue, large power surges on the nation's high voltage grid, and so on. So these reflections are kind of a problem. The way you stop them is just what we did in MATLAB. I want to terminate it with something that absorbs the energy. If I absorb too much energy, I get reflections. Don't absorb enough energy, I get reflections. Come up with the right number. They do that in buildings. In buildings, what they do is they put water tanks in the roof or mass spring systems on the roof. As the building sways back and forth, that dissipates energy with the water sloshing around. That dissipating energy helps reduce the reflections. You see that on circuit board traces. If I just have a wire on a circuit board trace that just ends, that's a reflection. You see that right here. I give it a step wave input. That causes waves to travel back and forth on the wire. Those reflections cause bouncing. If that bouncing gets too large, it passes through logic level 1, and I get pulse triggers. To stop that, I need to add a characteristic impedance, meaning a resistor at the end, to stop the reflections. Two courses that I highly recommend are Ben Broughton's Signal Integrity and Design for Electromagnetic Compatibility. The circuit board traces is actually an important problem that you face in industry. In industry, we have a lot of circuit board traces, a lot of circuit boards, and the clock frequency gets higher and higher. As the clock gets higher and higher, the circuit board trace starts to look more like a transmission line. So designing circuits at low frequencies is very, very different than designing circuits at high frequencies, like 100 megahertz. When you get to 100 megahertz or gigahertz, you need to take transmission line effects into account. That's what these courses are all about. And it's all about coupled second order differential equations, the wave equation. And one of our pride and joys at NDSU is we have the Governor's Shield Room. This room right here, the history behind it, that actually used to be the Governor of North Dakota's room. If you have a perfectly conducting sphere or metal box, there should be no electric fields on the inside. So that's what this is. It's a big metal box. And what it was designed for is if World War III would break out, the governor would go inside the room, close the door, be protected from electromagnetic blasts. They since decided they want the space more than the governor, so we got the room. What we do is you put your circuit board trace into here, close the door. Since this is a big metal box, any electric field that you measure comes from inside the room. So I can sit there and build the circuit, power it up, and see how much it transmits. At the end of the semester, I can redesign it after you take one of Ben Broughton's classes. Redesign it, see how much you reduce the radiation. It also works with duality. If you transmit, you also receive. I can put a computer into here, hit it with RF energy from an antenna, see how strong the field has to be until the circuit quits working. At the end of the semester, redesign it, see how much stronger the field can be before it quits working. That's kind of important because if you're building combines, you don't want your combine to shut down every time you drive underneath a transmission line. That's kind of what this room is all about. How do you design circuits from an antenna standpoint so they don't radiate and they also don't receive? So that's kind of the wave equation. The heat equation, kind of going back to MATLAB, is very, very different. The heat equation that we talked about last week is like an RC circuit. The heat equation, you simply charge a capacitor, you discharge it. That's the heat equation. Not real exciting. The wave equation, in contrast, is very, very different. With the wave equation, you get bouncing. If you have a long transmission line, you get reflections. And this isn't just in circuits. You see wave equations all the time. You see it in buildings swaying in the breeze. You see it on transmission lines galloping in the breeze. You see it in traffic. You see it on circuit board traces. So the wave equation is kind of an important equation. Those are coupled second-order differential equations. Or in terms of electrical engineering, think of the heat equation as an RC circuit. Think of the wave equation as an RLC circuit. The two behave very, very differently. MATLAB can be used to simulate both systems. MATLAB can be used to try to terminate an RLC circuit of wave equation to stop reflections. With MATLAB, you're using numerical methods to solve the differential equations. You can also solve them by hand, but to solve them by hand, I would wait until you take those courses. So that is lecture number 11 for ECE 111, Inductors. And with that, you should be able to solve this week's homework set.